All right. So, hello. A lot of you guys already catching on. I've got the link shown here, and maybe the QR code will work for you for the a quick little poll. I'll jump over to our syllabus in a moment once you've got that. I think it explains it in the poll, but the question for you is, are you interested in moving the exam date? And I'll come back to the link in just a second. From November 5th, as in the syllabus, to Halloween, October 31st. Now, a couple of you expressed great interest in this. That's why I was asking you. I don't mind at all, because what we'll do is swap the Flint water crisis behind the exam, and that won't really change anything on my end. That'll mean you can have the exam before fall break. Might be nice. Oh, excuse me. Never mind. Yeah, just before that weekend. Never mind. Not before fall break. But it could just change that date for you. So if you like that, that's the question. From the 5th to the 31st, and I'll rearrange the other part. And I'll look at the results with you here in a moment. And I think I gave you kind of like a yes, super please, sure, why not? Don't like that idea, but it's probably okay, or like no way. So if I get a lot of no way votes, then definitely not changing it. All right, anybody need another minute to get that? Okay. Just give me a thumbs up when you got it. Got it? Okay. Anybody else? All right. So let's see. Okay, so we've got 13 of you saying absolutely not, 9 of you saying yes, very much please. So that's I'm not going to change it with that. Just looking at that for you. Sorry for those that really wanted it. I appreciate your feedback, but I made the syllabus how I made it, and I don't know if people are making plans or what, but if more of you really don't want it to change, then really want it to change. It's pretty even, but yeah, that's I'm not willing to change it for that. So if you guys have a different idea or something, could think about it, but as it stands, I'm not going to make any changes. So sorry for those of you that wanted that. But thank you for your feedback. I do appreciate it. Okay. So last time we left off talking about some of the basics of units, things like that. Today I want to get into, all right, where are we putting those units? What are we doing with them? How are we taking action to treat water? So really, what are the actual reactors about? How do we look at them mathematically? And what are the reactions that go on inside of them? So it'll be useful for you right now to consider the fact that a reactor is much different than a reaction. So my water bottle could be a reactor. My stomach could be a reactor. There might or might not be reactions happening inside them, right? Hopefully there are reactions happening in my stomach, because that's what it's there for, right? Hopefully there's not too much happening in here, because it should just be water, mostly. Maybe a little bit of chlorine killing whatever might be in there, right? Just a little residual. So the actual reaction itself is very different than the container containing the reaction. So we need to distinguish these two and understand that mathematically we need to consider both, okay? Which makes sense logically if you stop and think about it. If you have something that's happening really fast, it doesn't really matter where it's happening, it's just going to be happening really fast. Now, on the other hand, we might be pushing water through some volume or some container quickly or slowly, that doesn't have to do with how fast a given reaction inside the water is happening, right? So the two can be completely separate, and we're going to combine the two to figure out the math about how our system might be changing. So a typical reactor might look something like this, and we'll describe each one of them more in depth. But on the left, this picture is a wastewater treatment reactor. This is an aerobic activated sludge system. Got a lot of air bubbling. It's mixing it quite a lot, and it's all brown and murky because there's a bunch of bacterial action growing a bunch of bacteria and eating the waste. That's the plan. So different reactions, different reactors, they're going to look all going to look different, but in some way we're typically going to have a flow-through system. Maybe we'll look at some batch systems that there's no flow. You just have what you have, do the reaction, and then pour it out. But in general, we work towards a flow-through system so we can have continuous operation. And if that's the case, then we're going to have some inflow, some outflow. We might or might not be mixing. So we're going to describe some of those types of things. Okay. So a few general terms here that we're going to use. Probably a lot of this is obvious, but I want to just make sure that we're on the same page. I'm going to use V for volume. That's probably cubic meters or something similar, maybe liters if it's a smaller system. Flow rate, I'm going to write as Q. That should be volume per time. It's the amount of volume of water flowing through the system. A concentration typically will be C. If it's chemical or something in a mass concentration, I'll generally be using C. If it's something like the number of bacteria or viruses, that's when I usually use N, maybe particles. C, we could also, instead of say mass, we could say moles, which is technically a number, but it's also a chemical, so I often just use C for that. So think C for a chemical or some mass concentration. I'm going to say or here, it's not the same thing. So really, I'll generally use C for concentration of a chemical or some mass of something that we're adding. That's not a hard convention. You could use, of course, any variable you want. I could call it X or C or B or whatever. But I'm just letting you know this is commonly how I will describe it for our class. Hydraulic retention time is another important topic we're going to be using a lot. In our book, we'll use the term theta for hydraulic retention time. It's also common to see it in tau, and I think I have a graphic here that uses it today. Hydraulic retention time is how long the water stays in a given system. So if we have water flowing into this reactor, it's swirling around, and some water is leaving at the same time. There's an average length of time that the water stays in there. And that's our hydraulic retention time. So this is, we could describe as the average time that a piece of water, the water, some water, however we want to describe it, that the water remains in the system. So if you think about putting a hose and filling my water bottle, just shoving the hose in there, turning it on full blast, there's going to be a pretty short residence time. That's another way to describe it, residence time. How long does that water reside in the system? It's going to be going in and going out pretty quickly, probably a matter of a second or two for the typical length of time that water is staying in here, and it's going to be spraying water everywhere. Now, if you do the same thing with a swimming pool, it's a much bigger volume. You can imagine on average, even if you're overflowing, you filled the pool and now you're overflowing, on average the water stays in there a long time. So it's literally defined as the volume divided by the flow rate. So big volume, big residence time. Big flow rate, lower residence time. That ratio is where you get it. And if you look, the units here, which we will look at units quite a bit, let's take cubic meters divided by the flow rate, which would be something like cubic meters per second, for example. So we divide cubic meters by cubic meters per second. That will give us how many seconds, right? So that gives us a time unit. So if you have any doubt about this formula, and by the way, this is one of those formulas, we'll talk about it again, but I'm not giving you this on the exam because you should just know this one, okay? Hydraulic resonance time, yes, you might have to commit that to memory, but it's so direct, so simple, so fundamental to what we're doing. I'm asking you to go ahead and know that. So that's the formula, right? Theta equals V over Q. So we see that. You can check your units. Does it turn out to be time? If yes, great. If you're inverted, if you got 1 over time, you flipped it upside down, right? That should come out to just be time because it's resonance time. Okay, so we'll use that. That's typically theta. Sometimes you'll see it as tau. That's the average amount of time the water spends there. Next up would be a generic rate. So we talked about flow rate. That's kind of the amount of water over time. Well, a rate, generically, we're typically going to describe for probably a concentration, maybe a mass. Ultimately, that's going to be, we're going to develop some rate equation, how that mass is changing over time. A lot of times we'll pair this with a volume so that it becomes mass over time. So if we take a rate in the context of a volume, then we get the mass rate of change. Okay, so typically we're going to start it as the rate of change for some concentration, dc dt, and describe that. We'll get into this more today in terms of how it depends on that concentration, and then we'll take that rate term and put it into the context of a reactor. So that's what we're going to do today. And then we have a rate constant, K. The rate is not the rate constant, but they're important to each other. And the units for K are going to depend on the rate order. Again, we'll cover that in more depth in a few minutes. So these are the big picture terms that we're going to deal with. And we're going to describe so that we can model and talk about these systems. And then we're going to use basically these tools for the rest of the semester. Sometimes we'll add some flavor. Sometimes it'll be a different context. Maybe we'll use it for something a little different. Or maybe occasionally we'll have systems where, well, we just need to model how gravity works, and we're not exactly using one of these, but it's these types of mass balances, these reactors and reactions, we'll see them quite a bit. Okay, probably 80 or 90% of our problems will have something to do with these reactors. Okay, so I want to start with the reactions first. So setting aside what kind of container we're dealing with, I want to talk first about the actual rate of something changing. This could be a chemical reaction, but it doesn't have to be. This could be a biological reaction. If I were to take all of you and say, okay, let's do an icebreaker, and then let's play some sort of game where you grab somebody's hand, and now you've got 2 people holding hands, and then those 2 people go and try to grab somebody else. Some game like that, well, that's a reaction between people. You're taking 2 units, or 2 separate units and forming 1 unit when you hold hands, right? You've probably played that mob game as a kid or something. We could describe even that as a reaction. Okay, so it's not that this is chemistry necessarily. Of course, chemistry can be a thing here. It could be, like the people example, particles sticking together. And we're describing that as a reaction. How quickly does that happen? How large does a particle become? That tells us how quickly it will settle out of the water, out of solution. Okay, so a reaction, then, we're dealing with the reaction term in our mass balance. So if a mass balance, we set it up for some system, the generic system being something like this. Last time we did one with 2 inputs, right? That's totally possible. I'm going to keep it simple for a moment and just generically say we've got inputs and we've got outputs and we have some reaction happening in here. Okay, so the reaction term then, what we want to say is what's happening inside there. Doesn't matter what this system looks like. The reaction term is going to be that part. We have 3 reaction orders that we can consider. And the reaction order simply means how does the reaction depend on how much stuff we have there. Now, that already probably doesn't quite feel like it makes any sense. So let me just take you to a real world analogy and say this is a lot like a bank account. If you think of your money as your concentration, you might have a system where you are adding $20 a week to your bank account. Doesn't matter how much money's in the bank account, you're just adding some flat amount, some baseline amount. That is a zero order reaction. It's some amount over some time. Doesn't matter how much is in there. Now, if you have interest and you have, let's say, 1% interest every year, if you had $100 in your account, over that year, you're adding $1, right? 1% interest rate. That's a lot different than if you had $1 million in there, right? Because then you're adding 1/100th of a million. So is that 10,000? However the math works out, you're adding that much, 100,000. Yeah, 10,000. You're adding $10,000 every year. That's a big difference because it depends on how much is in there. That's a first order reaction. We can do the same thing for the second order, meaning it relies on a factor like twice. So the way we describe that mathematically is the rate of change for something. In the bank account example, the rate of change for, let's say, the money in the account is equal to some change over time. That's just another way to say it, dc dt, right? Or d money dt. And we can describe that as either a plus or a minus. So maybe you're gaining interest, or maybe you're losing interest, or maybe you're adding income or paying some bills or something, right? Depending on how we want to describe it. A rate constant, in this case, my example was like a 1% interest, right? Or some amount per time. So this is our rate constant, does not change, times the concentration, or in this case, the amount of money in the account, raised to some power. So n could be 0. That's a zero order reaction. It could be 1. That's first order. Or it could be 2, second order. Pretty obvious, or self-explanatory. Now, in reality, there can be some gray spaces between, and weird chemistry or weird dynamics can happen. We're not going to go there. In fact, we're generally not even going to go to the second order typically. But let's take a look for a moment how the amount that we have would change over time for each of these. So I'll use growth equations. So let's say, for example, zero order growth would look like adding $20 to your account every week, right? Or every X amount of time. Maybe you have some in there to begin with, and over time, it increases linearly, right? Linear increase. For a first order growth, it's going to be exponential. If you start with very little, you're not going to get a big change at first, right? It's going to be a pretty small change at first, but as you get more and more, the rate of change accelerates, right? So it would look something like that. And a second order growth, it would be more parabolic, where you have, as soon as you're getting some there, it kind of shoots up. Of course, that all the speed and all that depends on the rate constant, but I'm not using specific units. I'm just giving you kind of an idea. So this is all just calculus you've seen before, right? You've seen the function of x squared. And if we're looking at the growth side of it, you know, on positive time, it looks something like that. So you've seen this type of math before. You even probably would recall that if we take the derivative of one of these, it's going to look like the other, you know, and we can move through them that way. And you wouldn't be surprised if I say we can also do, let's say, decay equations. First order decay would be pretty much the same thing, just a linear line. Pretend that's linear. And likewise, a first order decay would drop rapidly at first, and so on. So, and the second order, maybe I didn't draw that quite right. Try again. Okay, my drawing skills need a little work today. Okay, something like that. So you get the picture. So the reactions that are occurring, this is just the way we describe them: zero order, first order, second order, and it really depends on the exponent n there. Now, when we describe this for a system, let's say for your bank account, the k would then be a percent interest rate. And what we don't realize when we're talking about, let's say, APR, right? What does that stand for? Annual percent interest. The annual there means it's actually a per time value. So we get some ratio of what's in there over time. So for a first order reaction, that means like an interest rate, we are gaining interest based on some percent, that rate constant, and that rate constant has units of per time. So it's some percent per time. A percent is technically unitless, so it's just a number per time. So maybe it's 5% every year. So that is a great picture of interest rates. And the same would be true for owing interest on debt. It would just be a, opposite. You are, that's a decay reaction in some sense if you're paying that debt, right? So that's a very tangible, very practical example. And that just becomes 1. If n is 1, your first order, that means you've got your money times the percent. That's it, right? So we can deal with this mathematically. When we do it in a batch system, it's going to be very simple, as we'll see. If we do it in a flow-through system, then there's a little bit more complexity to it, and it's not quite so intuitive, but we can do it no problem. All right, any questions on that? Does that make sense? Okay, this is just as a reminder, this is all math that you've done before and have passed, and you've done more complicated stuff. Okay, so just to elaborate a bit on zero order reaction, and we'll get into the units here. Again, we have, it would look like that over time. Now, if we took the derivative, how is the rate of change itself changing over time? Well, it's not. It's always going to be some amount over time. So I guess I should draw a positive one. So if we have a rate of change like that, that means, well, the dc dt over time should be a flat line. It's always $20 a week or whatever, right? That part is not changing because the rate of change only depends on that constant. And we even call it a constant, and so it should not, the rate of change, the dc dt, should not change over time. So c to the 0 power is 1, so this kind of just goes away, becomes 1. Now these units are still here, and let's say c is in milligrams per liter, just as an example. So the units for c are still going to be milligrams per liter, or excuse me, no, they're going away, never mind. The k has to account for the c over here. Pardon my my silly thought there. So k has to capture the units of this. So whatever happens, the left and the right, the units have to make sense. And since we took c to the 0 power, that gets rid of the units. K has to account for the units now. So that means that K has to be milligrams per liter per time. So if time is in seconds, then, and C is in milligrams per liter, then K has to be concentration per time, milligrams per liter per second. All right? So long as I didn't confuse you too much with my misstep there. Should make sense, right? We just need to balance the units on the left and the right. If C goes away on the right, then it's just K needs to balance with that. All right, so we're going to do the same thing with the first order and the second order. So first order reaction, C to the 1 power. Again, this is going to look something like that. The dc dt, when we take the derivative there, is simply going to be now a straight line. It's not going to be flat, but it's going to be increasing over time just based on how the math works out. Right, so we can take the derivative of 1, the first order, and get to the 0 order, essentially. All right, so then the units here, this is, again, like the bank account, where K would be that percent per time. So it's really just a per time unit. Because we already have 1C on the right and 1C on the left. So then the K, all it can do is give us a per time value, and it must do that. So if we have milligrams per liter times K, and we need milligrams per liter per second, then K has to be per second, right? One over seconds. Does that make sense? Now, this is actually quite important. You will need to recognize this for problems on homeworks and exams, because this is how you know what reaction order to use when you do the mass balance. Okay, so this is relevant. You will see pretty often a per time unit. It's probably the most common, but you ought to be checking and watching your units, because you will need to know or be able to figure out, I give you some rate constant, you should know based on its units, is this 0, first, or second order? And you can. It's this simple, right? How many times does this reaction depend on C or N or whatever? Okay, so the same thing with second order rate reactions. We're not really going to use these very often. Doesn't mean I can't ask you something about them. It really is simple enough. You should be able to see this. It depends on C twice. There are some systems that do this. Some reactions, for example, if you have a highly reactive radical species, it can react with other stuff in the water, but it can also react with the same radical and kind of destroy itself. So some reactions are just so reactive, it's going to depend on that value to the square. So, and that's sort of the summary of it. In this case, we're going to describe dc dt as plus or minus K times C to the second power. So as we said, could be to K or growth, but it was going to look something like this. The derivative just looks like the first order, and so it's an accelerating change over time, and the second order change is that parabolic. Okay, in this case, the reactions for the units for K have to satisfy the fact that we have C squared on the right and just C on the left. So we need the per time. You'll notice we always need per time from K. And we also need to invert the milligrams per liter. So this reaction rate constant will look a lot like the 0 order because it has both milligrams and liters, but it's flipped because it's got to remove the extra milligrams per liter we have on the right, because we have milligrams squared per liter squared and K, whatever K is, and then milligrams per liter per second on the left. So K is per seconds, but it's also divide by milligrams and multiply by liters to cancel some stuff out. So that's why we get liters per milligram per second as the constant, as the units for the constant. Okay, make sense? It's not overly complicated, but it is important that you recognize this, know how to sort through what kind of rate constant are we dealing with when you have that on a problem. Okay. So let's talk about reactors themselves for a few minutes, and then we'll work on putting the math together for the different systems. We have three primary types of reactors, and these are, we will call ideal reactors. We can often have a non-ideal reactor that is some combination, or that we can model as some combination of these. So, for example, a swimming pool that is a long swimming pool might be a little bit mixed from the activity in it and from wind or something, but it's not fully mixed. The water at one end is not really mixing with water at the other end, so it's not fully mixed. It's a little bit between a couple of these ideal reactors, and maybe we say, okay, well, it's kind of mixed in the first third with itself enough. So we could say that's one, we'll call it CSTR, and then have a middle one and a third one, and then kind of piece together some series of ideal reactors to show the non-ideal one. We're not going to worry too much about that. Primarily, we'll be dealing with ideal reactors and sometimes sequence them and have some problems on that. So the three ideal reactors that we can use for a wider set of whatever other reactors would first be the batch reactor. That is simply something that is well mixed, and we do not have any flow. So great, water bottle is a great example, as long as we're mixing it somehow. So we've got some volume, it's well mixed within itself, and maybe there's some reaction happening. There's no flow rates, so the mass balance becomes very simple. It just depends on the reaction that's in that volume because there's no flow in or out. We'll talk a little more about that because that also means if there's a reaction, there's not steady state. There will be some accumulation upwards or downwards for whatever is reacting. Then we have a CSTR, which is basically we take that batch reactor and put a hose in and a hose out. Okay, so now we have a completely mixed container. The stuff that you put in at the left side of the container is immediately perfectly mixed with the stuff on the right. That's the assumption. Obviously, as engineers, we make a lot of assumptions, and sometimes we have to, account for that or deal with imperfections when it's not truly reality. But for the ideal, we will assume it's perfectly mixed. Okay, so then that means as soon as we add some water in there, it gets completely mixed. So if we have some reaction decreasing a concentration, maybe we are destroying some contaminant, as soon as we add some water that has a lot of contaminant, we are going to dilute it. Meanwhile, that reaction is continuously reducing the concentration. That also means whatever's leaving is exactly the stuff that's inside it because it's so well mixed. Whatever is inside there, the current concentration, is the same stuff that's leaving. It's a little bit funny to think about sometimes, but it's kind of like a drop-off if you're removing something. The reaction is happening continuously. It draws down the concentration, and you're adding stuff in, and whatever's in there is what's leaving. So we'll talk more about that. But this would have a flow in and a flow out, stuff mixing, and in a very simple case, we have no reaction. That's the problem we did last time, right? So we had two inputs. Those are the combined, we have an inflow term, or in that case, we had two that we combine into one, and an outflow. Often we will have a reaction, because that's kind of what we're interested in. But in the simple case, we already did one of these problems. Okay, the last one is what we call a plug flow reactor. And by the way, I guess I didn't write these. I'll back up a step. CSTR, that stands for continuous. If I can spell, would be good. So continuously stirred or sometimes people will call these a CFSTR, continuous flow stirred tank reactor. Tank reactor. The book uses CSTR. That's what I'll use. You'll see maybe CMFR is continuously mixed flow reactor or something like that. There's a few ways to call them, but it's a batch reactor with an inflow and an outflow. Okay. Then the plug flow reactor, PFR. You can think of this as a long, thin pipe, something like that. A conveyor belt is another reasonable example. It's going to convey one person on one of those steps across until they reach the end of the conveyor belt. Whatever reaction might be happening is going to be siloed into there and not mixing with the other people on the conveyor belt. Or like when you have a hose on a hot summer day and you're a kid and you want, let's say you're going to drink from the hose or fill a water balloon or something. You turn on the hose and it's been sitting there in the sun, and so for the first, feels like a minute, it's hot water because it's just been baking in the sun. Suddenly, there's a step function where suddenly you get cold water. That water is not mixing within the hose from the beginning to the end, right? Otherwise, it would have started cooling a little bit immediately. Instead, the water that was inside or in the ground, in the pipes, once that reaches the end, it finally comes out and it's big change right there. Suddenly it's cold. So that's the type of dynamics we're talking about with a plug flow reactor, where we're not mixing from one end to the other. In fact, we'll treat it as one little plug. Plug of water is flowing through this reactor, and whatever's happening inside that plug it's essentially well mixed in there and not with the neighboring parcels of water. Okay, so that's the kind of the concept for a PFR. So think of it like a pipe or a hose. So that means we can have a reaction there where whatever's happening, it's almost like we take a little batch reactor, let's pretend, and put it on a conveyor belt, and whatever's happening in there, it's not mixing with its neighbors, it has some amount of time to react, and then we're pouring it out, essentially. So that's going to change the dynamics of how much concentration is in there and how much time that water has in that particular reactor. Now, our hydraulic residence time is still V over Q in either case. But in the case of a plug flow reactor, the fact that it's not mixing makes a big difference. Okay, so we'll take a look at that as we go. Okay, so about batch reactors in particular, so elaborate on each of these real quick. We have no inputs, no outputs. So if we have accumulation rate is equal to inputs and minus outputs plus reaction, these both go to 0, right? Because for a batch reactor, we have none of those. We assume perfect mixing. So maybe we have a mixer in there. That means our accumulation rate is simply equal to our whatever reaction might be happening. So when we write the accumulation in some volume, we could write that as volume times dc dt equals 0 inputs minus 0 outputs plus the reaction term within that volume. We would say the volume times the reaction of C. Okay, here's where we would call back to what we learned a few minutes ago, based on whatever reaction order we have. That R of C, that's dc dt, that is going to have some rate constant and depend on the concentration some number of times, right? Depending on the reaction order. So that's where the reaction term comes in. So in that sense, we can write this as V dc dt. Now, let me just pause a moment and say accumulation. Let's remember what I was talking about with that. Accumulation, this could be how much money is in your bank account. The bank account being the reactor, and it contains something. And you're looking at how is that changing over time. I used the case of a swimming pool that you're filling up, where water is the C, how much water. That might get a little confusing because normally we're not going to accumulate water. We're just going to assume it's already full. Okay. Maybe we are adding salt to the water until we get the right salt concentration for a saltwater swimming pool. Okay, how about that? So then over time, we are adding a certain amount of salt. Then we are accumulating that salt. Perhaps, yeah, so that might be a reasonable example. So it's the amount of that substance within that volume is how we describe this. So V dc dt ends up, the units become volume times the mass, let's say milligrams per volume per time. So the volumes will cancel and we'll get a mass per time. If you remember last time I said, I'm just going to call this mass. I said almost all of our rates are ultimately going to boil down to a mass per time. This is how it happens for an accumulation term. So we're going to have that accumulation in that volume. That's what we're looking at. So that's my point here. So when we write the accumulation rate, V dc dt, we can set that equal to our reaction term, V times that reaction rate. The volumes will cancel, and so the accumulation is only equivalent to the reaction. Now, we might have positive growth reactions and negative growth reactions. So it can be a little more complicated, and maybe we could reach a steady state where there's zero net accumulation if we have something producing and being destroyed at the same time. So this could be growth, could be decay, could include both. Those are all options, right? We can have multiple reactions happening. Just like we had multiple streams coming into one spot in the problem last time, we could have multiple reactions also. A lot of times we're just going to look at one, but there's nothing stopping us from having multiple reactions, okay? That's the spot they will go in our reaction term. So if we have just one reaction in a batch container, the accumulation cannot be zero. That's just by definition. Okay, so we'll say usually not at steady state. So steady state is when our accumulation term goes to zero, meaning we've reached, maybe something's happening in there, but we've reached a spot where it's steady. It's a constant amount of whatever is happening is happening. So typically, or excuse me, no accumulation. So typically not at steady state unless no net reactions, I guess we'll say. So maybe no reactions at all, or maybe counterbalancing. Does that make sense? All right. So we'll go to the CSTRs, have it spelled out for you here. So these have a continuous input and also continuous output. Those, in terms of a water basis, should be the same. It would be really strange and a difficult task to work with a system where we are adding in 5 gallons per minute and removing 10 gallons per minute, right? We're draining the system in addition to trying to do other stuff. That's not how we're going to operate any system practically. We're going to do something to keep the flow rate the same, because that should be easy enough to do. Sometimes wastewater treatment plants will have an equalization tank where they can accommodate a larger flow rate coming in and let it kind of stabilize there and treat a constant amount of the wastewater over time. So sometimes you'll have cases where you might manage the flow rates a bit, or you have to, but generally we're going to design a system so that we can have a constant flow rate, right? It doesn't make sense to overflow our tanks or to deplete them. We just want that that part should be constant. In a CSTR, we're also going to assume perfect mixing. And so then our accumulation rate, we're going to describe V dc dt. If we have some flow rate coming in, like I just said, we're going to have that same flow rate going out all the time. Keeps it nice and simple. Then we're going to have some concentration coming in and some concentration leaving. I will call it C naught or C initial coming in, and C just for C final. We could also describe, so of course this is in some volume, we could also say that the C inside here is just the same thing because it's perfectly mixed. Whatever's in there is the stuff that's coming out. Okay. If we have some reaction in there, then C is not going to be equal to C naught, if that's changing. So we're going to describe this whole system then as Q times C naught minus Q times C plus whatever reaction term is happening inside that volume. So we'll give a V here times R of C. Now, just like last time, R of C, I'll be a little more elaborate this time. We'll say that is plus the growth reactions and minus whatever decay reactions we have. So it'll be as many as we want the growth reactions and as many as we want the decay reactions. But that reaction term will capture all of that. Okay. And then we'll put that in the context of the volume that we have. And by the way, we could have a first order growth and a zero order decay. So that kind of stuff can happen. It's maybe not super common. A lot of times we'll just deal with one at a time, but there's nothing stopping us from doing multiple. Okay, does that make sense? Good on that? And you can see now that when I'm describing the reaction rates here, this is kind of a blank spot where we can plug in the reaction orders information into any one of these spots. So we have a reaction order that can go into here and give us a specific result for the mass balance. This is what I'm talking about when I describe a mass balance, right? This general equation and how we develop that into specific variables and then ultimately numbers is this, right? So you have to know that the accumulation rate, we're talking about that in the context of a volume, and that's simply the rate at which it's changing over time. V times dc dt. That's our accumulation. That's the left side of the term. And this is our mass balance. Now, we'll say if the accumulation is 0, that's what we call steady state. And what you'll notice is if you were to try to do an integration for this problem with V dc dt equals all this stuff, it gets a little complicated. It's not impossible. But if we take it to steady state, that becomes 0, and we can solve for one of the parameters. Maybe we're solving for the concentration. It becomes simpler, and we don't really need calculus for that. It's just algebra at that point. So it's very convenient then to operate at steady state. Both mathematically and just operationally, we often aim to get at steady state for these continuous flow reactors. It's pretty convenient that way. Okay. So on to plug flow reactors then. These are a bit different. There's a few ways we can describe them mathematically. We could look at, for a given plug, and this has some thin volume, like really we describe these plugs as like almost an infinitely small volume. So if we look at it like a cross section, it would just be infinitely small little guy right there with a flow going in and a flow going out and completely mixed within that plug. That's the ideal reactor system. That means we have an infinite number of CSTRs in a row. So you probably remember from calculus, there's things like, there's different expansions, Taylor expansions and stuff, where you could say, okay, if we have this happening and do it an infinite number of times, we get this other shortcut and magic math happens, right? So we could look at it that way. We could derive the math that way as well. A simpler way to think about it is to say, okay, each one of these plugs is a batch reactor, and I'm just going to put it on a conveyor belt, and it's going to be an infinitely small reactor, but it's still just going to be on that conveyor belt. And so whatever's happening to that batch reactor over the course of time it takes for it to go through the reactor, which is the hydraulic retention time, that's just the same math as it would have been, right? So really, we just described this as a batch reactor, but instead of deriving the math in terms of time, that we just let it sit there, we're going to use the tau here, or the theta, hydraulic residence time, as the time dimension. So we do a batch reaction for X number of minutes because the residence time in the reactor is X number of minutes. Okay? It's almost the same thing as if we just filled this up, started a reaction, and waited 5 minutes. Instead, we make a hose long enough to have water continuously flowing through it such that it takes 5 minutes for the water to flow through that hose. So it's very simple to treat this as a batch reactor. We just have to make sure that we're treating the time as time equals our tau, or I'll say theta for our usage. We'll use theta. So that's what our primary book uses. Does that make sense? It'll make a little more sense when we start looking at the math to say, okay, how do we solve this? What this means is the whole system could find a steady state, but each one of these batches, we probably are not at steady state. We probably have some reaction happening, and within that batch, it's not at steady state, but we can model it with the batch kinetics and batch modeling, and it's very conveniently goes to the end like that. So the assumptions: we have continuous input and output, we have complete mixing within each plug, and no horizontal mixing between the different plugs. Of course, these are, again, assumptions, but this is the ideal reactor. The ideal plug flow works that way. Okay, all set on that? So now we have 3 reaction orders and 3 reactor types to deal with, and that's kind of basically it. Any reactor can have any number of reactions in it, and they can be any reaction order. A lot of times we're going to pair them one-to-one. What I don't want you to do is to think that, oh, whenever we have a CSTR, that's always a first-order decay. We will do a lot of those, and so you'll get used to seeing the resulting mass balance that happens when we solve for a steady-state CSTR with first-order decay. That's going to be the one you see the most. You might even commit it to memory just because. But what I want you to be able to do is to be able to derive that based on these principles. None of what I just described to you is super duper complex, right? You've seen all of this math before. You know how to work with units. Putting it together will be more complex. So it might take some time, but you can do each one of these steps. That's my point. I'm confident of that. So I'm hopeful that you can piece these together, always using this overall mass balance, accumulation, got inputs, outputs, and some reactions. Okay. Little elaboration on hydraulic residence time here. And I also have a video to kind of show. There is a thing called tracer tests. Let's go ahead and play this. So a tracer test is a way to like experimentally see how long water stays in a system and the flow dynamics. And so this is kind of an example of one just moving through here. You add some dye and you watch it go through the system. So this can kind of help us see, okay, is the reactor ideal? How long does it take? What's that residence time? So this is pretty slow residence time, as we see. And this is, we're not going to deal too much with tracer tests for our class, but it's a way to handle the non-ideal reactors. And you can even see that the mixing here is not really ideal, because you see some patches that don't really have much of the dye, some patches that have a lot of the dye. So it's definitely not an ideal reactor, but it's acting a little bit like a plug flow reactor, right? And as we play it, you'll see some of the dye at the center is maybe it's diffusing forwards a little bit, mixing a little bit with the water in front of it. And some patches, just after this corner, for example, it's not really seeing any of this dye. So if this dye was a disinfectant, for example, the water that's in contact with it gets disinfected better than the water that doesn't. So the fact that we might have some dead volumes, it can be important for a few reasons, including the water just on average doesn't stay there as long as we wanted it to. Okay, so we talked about hydraulic retention time. This is just, here it is again with that tracer test example. That's what we're talking about for the volume over the flow rate. Now, if we look back at our typical mass balances, we will find that we have several flow rates on the right and a volume term on the left. If we divide everything by a volume, and we typically have a volume with the reactions, we'll end up with a lot of cases where we have Q over V, which is 1 over hydraulic residence time, or we could divide everything by Q and get hydraulic residence time. So we'll see it show up as a shortcut in our reactor, in our mass balances quite often. We don't have to do that. It's simple enough, but you'll see we'll find the theta pretty frequently as a shortcut. Okay, so let's get on to some mass balances. So for a batch case, again, this is just a container. This is just no inputs, no outputs. It's well mixed. That's it. All right, we have some volume. We probably have some reaction, and it's mixing. No flow rates, right? That's the batch. On the left, let's do a zero order decay. So take just a moment and think about this for yourself. Challenge yourself. Can you derive, using a zero order decay reaction, a mass balance that finds an equation for C? C equals what after some time? So we can maybe write that C of T or something. But can you do that? I'll do this with you in just a moment. I'm going to give you time to think about it. Okay, so hopefully if you got it started, you would start with the overall mass balance, right? The accumulation rate, and we put in a term for that. So accumulation should be in that volume, the dc dt. So always start there. And then we can set that equal to the inputs and outputs. These both went to 0 because we have no inputs or outputs. And then we have the reaction term, which also has to be in the context of the volume. So then we have zero order decay. So we would say minus V times K. And if you want to, we could put C to the 0 power, or just recognize this goes to 1. So we could leave that off if we already accounted for that. That's the piece that goes in there. Right, so I hope you approach your mass balances with that kind of approach, right? So this, you could even write 0 minus 0 plus the negative V times K times C to the 0 power. So you can be very elaborate about it if you want to. There's no problem with that. Okay, so from here, we just have to solve and do the integration. Pretty simple one. So we divide both sides by V. We get dc dt equals minus K. So we can separate and say dc equals negative K dt. We'll integrate from 0 to time t. And we'll integrate the left from some initial condition C naught to C. We almost always have some initial condition, right? So we can just use C naught for that. So this should be, just resume here, C minus C naught equals minus K times T. So the T at time 0 is 0, so that term goes to 0 when we multiply by K. And so we can say C equals C naught minus KT. Could arrange it differently too. So pretty straightforward. Probably seen this a million times, velocity terms and stuff like that. You could also solve this for K, right? Just do a bit of algebra. So I said solve it for C, or how about T? You could put T in terms of the other stuff. We're using the mass balance to solve for something we're interested in. Maybe we're designing a reactor and we will just want to know, well, how long does this reaction have to go until we get our desired result, right? That could be the question. So don't limit yourself to saying, oh, this is the solution. This is the setup, and then we can find some solution that we're interested in, okay? That's the way to think about it. All right, so how about a first order decay? This one you will run into just a little bit of calculus, but again, you've done it before. So give this 3 minutes and see how far you can get. Yeah.
When you said C is 1, so how do you do the unit of C?
So in this case, when I said C is 1 or C goes to 1, that's because I said it's a 0 order reaction. And that means that in our reaction rate, so our reaction equation here, the C to the what power? So in a first order reaction, the C is to the 1 power. In a 0 order, the C is to the 0 power.
Yeah, but it doesn't have any unit to the 0.1, but we have to worry about unit.
You should be aware there are units. You didn't have to in this to solve the mass balance. But you'll notice the units, like the K here, you'll notice the units actually have to be, and this is a great question, they have to be milligrams per liter if C is milligrams per liter. They have to be the concentration units divided by time, because the units here have to be the same as the units here. It's not an appropriate, you can't subtract apples from oranges, right? You have to end up having the same. So you're exactly right to look at that, and you can check that the units, if C is in milligrams per liter, then the K would be in milligrams per liter per time, whatever the time units are. So you're exactly right. right, so hopefully you started this one as accumulation rate. So V dc dt equals no inputs, no outputs, 0, 0. Plus in that volume, you have some reaction. This is a negative again, it's a first order decay. So negative K times C to the 1 power. Okay, something that looks like that. Now, in this case, again, we can cancel the V's. So the next line would be dc dt equals negative Kc. So pretty simple. So now we need to integrate. I'm going to move the, I'm going to separate by parts and get C's on the same side and move dt to the other side. So we'll remember that we could set this up as dc divided by C equals negative K dt, and then integrate. Now, here's where you have to remember just a bit of calculus, but like I said, you've done this before, so this part should be quite possible. We're going to do this from C naught to C again, and we're going to integrate this from time 0 to time t. So on the right side, it's pretty obvious this is just minus kt. On the left side, does anybody remember what this comes out to be? Natural log, yeah. So the integration of 1 over x dx is the natural log of x, right? So you've learned that before. It's probably been a while, and I don't fault you for forgetting, right? That's just the way of it. So what we end up with is the natural log of c, but we have to go from c to c naught. So we end up with the natural log of c minus the natural log of c naught. Now, again, something you've learned before but may have forgotten, this is algebra this time. With logarithms, if you have log of something minus log of something else, you can actually merge those two and divide. So when we have natural log of c minus the natural log of c naught, that's the same thing as saying the natural log of c over c naught equals minus kt. What you'll find in just a moment is this is going to be looking more and more familiar, and we've basically derived what you probably learned in Algebra 1 some long time ago for describing the interest rate of a bank account. Okay, and so, but this is we're doing a decay here, so this would be negative, but that's you might have called it the PERT equation. The principal equals e to the rate constant times time. So we'll see that come out of this here in a moment. So we might not like dealing with the natural log, especially if we want to find c, like we said. So we can say, let's get rid of that by taking both sides and taking e to the power of what's on the left and e to the power of what's on the right. That'll get rid of our natural log. So we take, this becomes c over c naught equals e to the minus kt. So another algebra logarithm trick. And then, of course, we can, from there, go to c equals c naught times e to the minus kt. And that's the form you've seen probably a million times. Whereas in the finance, when you learn that, it was probably P equals RT, something like that. That would be the result if we did a growth equation, first order. So, like I said, these you've seen things like this in other systems, but now we've been able to derive it for what's happening with a reaction in water in a container, right? That's the deal. Becomes pretty simple. There's a little bit of algebra calculus to remember, but if you get this part, that's just about as much as you'll need. Occasionally, when we have non-steady state systems in the CSTRs, we might go a little further. Now, this is exactly the same thing we need for a plug flow reactor, except instead of waiting for some time t, we would use theta, just because that's the amount of time we have as it goes through our pipe or through our reactor. So we can do exactly this thing, this process for 0 order, first order. Could also do this for second order. I'm not going to bother you with that here, but we could do it, and we could get the same exact treatment and apply this to a plug flow reactor, just making sure that we're using theta instead of some arbitrary time, right? And that's the decision, right? So then the good thing about a plug flow reactor is we don't have to sit here, fill up a bottle, wait for some number of hours and pour it out. A good practical example of when you see that actually in place is for winemaking and brewing different beverages. You'll maybe store it in a barrel for some amount of time. That's a batch reactor, and you're letting a very slow reaction happen over the course of some amount of time, aging the wine or whatever. And then you're going to pour it into other bottles where the reaction is no longer happening, basically. So there are some real life examples of that. Okay, so then the last one, because now we've covered batch and plug flow reactor in one, the last one is going to be the CSDR cases. I'm going to get it started, and we probably don't quite have enough time to finish it, but take a look at the zero order one, and again, start with your accumulation. We'll have a Q in and some C concentration going in into some reactor. It is well mixed with a Q going out and a C going out. There's some volume to that, and the concentration in there will be a C. So take a moment and start working that zero order case. I'll finish that out in a minute, and then I think we'll start on the first order one next time. Go ahead and put this one in terms of C also. Oops. Okay, I didn't say this yet, but most often we'll do these ones with steady state. So what you'll notice here, I will solve this for you in steady state. We can solve this non-steady state. It's just not as typical, and that sometimes requires a little more calculus, some U substitution on occasion. Sometimes they get a little tricky, so probably we're not going to do too much of that. But I'll go ahead and say here, for the sake of the example, assume steady state. That would put our V dc dt to 0. So then we can say 0 is equal to Q C naught minus QC. So minus VK. Hopefully you started setting up an integration. And I think in this case that it's probably simple enough you probably could have done it. But You could have done exactly like we did in the batch one. It's just a few more variables floating around. If we have steady state, it becomes even more convenient, and we can simply add the QC parameter to both sides and say QC is equal to QC naught minus that VK, that reaction term in the volume. And here now we just divide everything by Q. So C equals C naught minus V over Q, which, if you recall, V over Q is our hydraulic residence time, right? So V over Q times K, or we could say C naught minus theta K. Okay, so if we're at steady state and we have one input and one output and one reaction that's a zero order decay reaction, that's always going to be true. And we'll find a similar relationship when we do the next part next time. But what I want to show you here is that was a lot of ifs. So on a problem, on an exam, for example, maybe you memorize, okay, here's the end product for my mass balance if X, Y, and Z are true. Maybe you can get away with that sometimes. But the point here is to be able to start from the mass balance, the governing equation, as we might call it, and build a mass balance based on what you need. So that's what I hope you learn, rather than just trying to memorize and hope you get the right one and get all the pieces right. Okay, we'll see you on Thursday and pick up here.